Alright, so propositional logic, it's also known as sential logic. It deals with propositions and their truth values, and this is a fundamental aspect of logic used in mathematics, computer science, and philosophy. So, a proposition is a statement that can be either true or false, but not both. So, an example could be this is a true statement. So, the basic logical connectives are and, or, not, implies, if and only if. So, and looks like this, or looks like this, not looks like this, implies looks like this, if and only if looks like this. And another one I forgot was exclusive or, which is this, or sometimes like this. So, and is only true if P and Q are true. So both P and Q are true. So if we have P and Q and we draw out the truth table for this, so true, P is true and Q is true. P and Q is true. True, false, that's false. Same thing, this is false. False and false is false. P or Q is true if either P or Q are both true. So if either one of them have a truth value, then it is true. So P and Q, true or true is true. True or false is true. False or true is true. False or false is false. Not P would basically be the opposite of the value. So true becomes false, true becomes false, false becomes true, false becomes true. Now implies, P implies Q. So first, so P implies Q is true if whenever P is true, Q is also true. So if we first look at P, check if it's true, and then Q is true, so that's true. But if we look at this row, P is true, so we look at Q, and we see that it's false, so it's false. Now, these ones, P is false, so they're just going to be true anyway. And the biconditional statement, if and only if, this is true if P and Q have the same truth value. So true and true, that's true. True and false, that's false. False and true, that's false. False and false, that's true. And exclusive or, P XOR Q is true exactly one of P or Q is true, but not both. So P true, Q true. So if we're looking at these two columns here, so that's going to be false, since only one can be true. True, false, that's true. False, true, that's true. False, false, that's false. Those are the basic logical connectives that we need to know. Alright, so here we are asked to construct a truth table for P and not Q, or Q implies P. So first I'm going to start out by writing P Q, and then I'm gonna write the possible values for P and Q. Now for not Q, and now we do this part of the statement. So here we're only looking for P and not Q, so these columns here. And we gotta AND them together. So true and false is false. True and true is true. False and false is false. False and true is false. Now we do Q implies P. Now we are looking at first this row and second this row. So I'm first going to look at Q is true. An easy way for implies is to look for when Q is true and then see when the second one is false. So this row here, I know this is going to be false, and since there's no other occurrences of this, everything else is just going to be true. Now we do the full statement. So we're looking at these two here. False or true. False or true is true. True or true is true. False or false is false. False or true is true. Now, is this a contradiction or a tautology? If we look at these values in these rows, for it to be a tautology, all of them need to be true, and for a contradiction, all of them need to be false. But since that's not the case, it is neither. So in this question we have to prove that this statement is a tautology. So we have to basically prove that this is true using the logic laws. So let's start. So if we look at the logic laws, we see the implication law here, and we see that there is an implies on the outside here. So we can apply this logic law now. And we have to also write which law we used. Alright, so the next one I see is this not on the outside. So if we look here, we see the De Morgan's laws, and we can basically use this now. So yes, we have to flip the symbol when we have to flip the and to an or when we use the De Morgan's law. Now we can see that these are both ors, which means we can use the associative law here to move the brackets basically. So we can do something like this. And once again, I'm going to use the implication law because there's an implies here. So this one right here. Now we can see that these two are basically identical. So we can basically imagine these as P and Q themselves. But if we look at the laws, if we look at the inverse law, we can see that P or not P equals true. So this not here implies that. So this just becomes true now. Therefore, it's a tautology. Alright, so this question is asking us to prove that X implies Y is logically equivalent to not Y implies not X. So let's start on this by writing it out. And then, so we can use the implication law. So it'll be not X or Y. And since the X is on the opposite side, we can actually move the X to the other side. Since this is an OR here, we can use the commutative law to do this. So this one right here, which says P or Q is equivalent to Q or P. So we can basically do this. Now we are actually getting closer to this statement. And we have to somehow get a not Y here. And to do this, we can actually go in reverse. We can go backwards with the laws. So this double negation law, we got not P is equivalent to P, and currently we have a Y, so we can actually just use the double negation law and add a not here. So not Y or not X. And now we can go backwards again using the implication law to say not Y implies not X. And we have arrived at our final logically equivalent statement. So these two are both logically equivalent.